Hello, we are here for another video. It's about geographically weighted regression. And the first step is to perform the grid search in order to find the optimal bandwidth before fitting the model. So the GWR, or geographically weighted regression, is implemented in Python. That's Jupyter Notebook here, using the MGWR, or multi-scale geographical weighted regression package. And the purpose is to model non-stationarity by fitting local models, so the local coefficients, local R squares. So MGWR is a specialized library for the M for standard geographical weighted regression package. So as I've already said before, the function select for cell BW, so select band width, is used to find the optimal bandwidth before fitting the model. So it's the grid search part of it. So this is what we'll be doing in this video, and the purpose is to find the optimal, the best bandwidth to minimize criteria like the AIC, AKK, information criteria, or cross validation. And the default criterion is the AIC. So to perform the geographically weighted regression, generally you need coordinates, you need your dependent and independent variables. When you have your bandwidth very small, it captures local variations, but it may overfit sometimes, while a large bandwidth approaches global ordinary least square. So here in the result you will have two results. In the summary of the model we have two results. The first one is about the ordinary least square, that's general model, and the second is about the GWR. So as kernels you have Gaussian, by square, and exponential. The commonly used are Gaussian and by square. So let's go to Jupyter Notebook and start working. So you need to install packages, necessary package libraries, you import them, install them before. So you need pandas, you need GeoPandas, you need libpython, and then you need your MGWR, multi-scale geographically weighted regression. So you install them either in Anaconda prompt or using command prompt, or you go to Jupyter terminal and then you import them. You need to import NumPy, import pandas, import GeoPandas, import Shapley.geometry. From Shapley.geometry you import points, this for the coordinates, and your libpython, and then our GWR, and the cell BW. You have warning issues or some, you import warnings in the warnings ignore. So let me run this. and the data set is found here on my computer in this directory. It calls wells 3. This is it's a CSV file. So let me add more cells immediately. Okay, what is in wells 3? Let's look at it. Data dot head sorry, add e before a. Okay, so you have the x coordinate, y coordinate, we have depth, we have pH, we have SO4, NO3, and T. Sulfate, nitrate, T is for temperature, pH is potential in hydrogen. Okay, so we need a geodata frame here. So we need to transform this data set into a geodata frame. First, we need to pandas data frame. So let's call it df equal to p dot data frame data. This data frame. Pandas. And then the geodata frame, we need a geometry. Geometry equal to point xy for xy in zip df dot export df dot y core. We close the parentheses, you close the brackets. Let me verify. Okay. So this is setting up the geometry. Then the geodata frame itself, let's call it my data equal GPD, so geopandas geo data frame. Oh, pandas data frame, and our geometry we just set above geometry. Geometry equal to the geometry we set above. Then the coordinate reference system equal to EPSG port 326. Then we close the parenthesis. Okay, so this is the geodata frame we need. Okay, so let's check what we have in our geodata frame. We have a column for geometry. So this is what we get, the column for geometry, which does not exist in our data frame. Let's have df.head as well. Okay, so the data frame, from data frame to geodata frame, you have one more column added to the data. So now let's prepare our input and output data. Preparation. Let's start with our output. So the dependent variable which is y, and y here we're going to use pH. So y equal to my data, we take pH, potential in hydrogen, so dot value dot reshape, need an entire array here, from -1 to 1 we have two parentheses rows here. So let's check the first 5 rows of y. But let's see, don't worry, so long. Y dot head, let's see. Nope. No. So y dot shape, sorry. Okay, we have 100 rows for one variable, which is pH. Okay. So let's have the independent variables, which the independent variables x, I take both T and the depth. T is temperature and depth is the depth of the well. So total depth of the well. So x equal my data. Sorry, brackets instead of curly brackets. have T, the temperature of the water in the well and the total depth of the well. So dot values, so let's have x dot head, x dot shape, sorry, and then we print x. Let me see. So we have these two columns here. We have here temperature, and here the total depth of the well. Good. Now we need the coordinates. Coordinate, we have the longitude and the latitude. Have u equal to my data x. We take from my data x coordinate. Score. Okay. That values. These are longitudes. And then we take from my data the y coordinates. And this are the latitude. Then we need to put them together to have our long lat columns. So chords is for the object chord equal numpy that array. We have list zip u v 1 2 3. Okay, this is the long lat. Okay, so let's print and see. Let's have the shape first. For course dot shape, we have 100 for two variables, the longitude and the latitude, and the course dot print print not print course. So this is what we have, long lat coordinate. Sorry for the noise. Okay. So we already have our input, the output and input data prepared. We are going to perform the grid search. Let's say loading the data is one step. So this first step, second step is the data transformation, and then third step is the data preparation, and then we are at the fourth step here, which is the grid search. The fourth, performing the grid search for optimal bandwidth. Using cell underscore PW. Okay. So as I already said before, for kernels you have Gaussian, bi-square and exponential, the criterion AICC and CB. Cross validation. So in this tutorial we are going to use Gaussian as kernel and the criterion is going to be our going to be is cross validation. So we need the selector equal cell bandwidth, so select bandwidth, parenthesis, coordinates, we have our input pH, we have x, sorry, our output y and x, the input, and the kernel equal Gaussian multi equal to false. So this is the selector. After having the selector, we need the optimal bandwidth now. BW, optimal bandwidth equal the selector dot the search criterion equal to CV, cross validation. Searching an optimal bandwidth. So here, depending on the size of your data sets, it's going to take some time. I reduced to 100 for the sake of this video. So more data have more time it's going to spend. So it's running, but let me continue. typing the code. So we need to print our optimal bandwidth. The optimal bandwidth is opt underscore BW. This code is going to print our optimal bandwidth, or just by tapping opt BW will get it. So now we'll take an example. The optimal bandwidth we get to fit model. Fitting the model using the optimal bandwidth. Identified or obtained in step. This is step 5. Instead of 6. Obtain in step 4. Okay. So the first thing, as usual, initialization. You initialize the model, then you fit it. So let's say model equal to GWR. We have course. We have the output. We have the input variables. We have bandwidth equal. So we wait for this step 4 to complete. It's still running here, so we don't wait. Busy. So when we get the answer from here, we put it here. From there, we put it here. So, and the kernel is pushing. Okay. We fit the model. Oh, sorry. Insertion, fitting the model. Let's call it GWR underscore model equal model dot fit. Of course, put X or not to get the same result here, and then we print the GWR underscore model dot summary. It's going to give us the summary of the model. Okay. the results of our model. That's step 6. GWR model analysis. We need to add local coefficients to the data frame. It's geodata frame here. Let's add the first one, the intercept. Okay, so the model it says here that's already finished. So let's get the result here. The optimal bandwidth says that's 54. So the optimal bandwidth here is 54. So you put it here. BW equal 54. Then we run. Then we go to the next. We fit. Then we output the summary of the model. Okay, this is the summary, the model summary. It's the information model type Gaussian, number of observation 100, number of covariance 3. So an input and an output and 2 inputs. This is the global regression result. This is the ordinary least square with the coefficients. We have the intercept here, we have temperature here, we have depth here with their estimate, standard errors, p-values. You see here all the information, and what's important here also is r square. And I just set r square, everything AIC, AICC, BIC. And below you have geographically weighted regression result. So it gives, I said it before, it gives 2 information, OLS and GWR. So in GWR we selected the special kernel, Gaussian, bandwidth we got 54. Diagnostic information we go through it, and you see the r square is a little bit higher here. It's 19% here. Yep. While with the ordinary least square we have r square which is 0.09, so less than 10%. Okay, and you have all your other information you need. You have the estimators, the summary statistics below here. Okay, so now you want to add the intercepts, local intercepts to the data frame or geodata frame. So let's say my data. Let's call it GWR intercept equal to our model is called GWR underscore model. We are going to take the parameter, so the params and the intercept, the index is 0. So no, it's not semicolon, it's colon rather. Yep. So this is the intercept. The intercept, local intercept, the local intercept values. So let's have your t values as well as our depth values. Local coefficient values. T local coefficient equal to WR underscore model dot params, and we know that it's the index is 1 for temperature, x1, x0 intercept, x1 is t local coefficient values. That is change intercept. This one. Bracket instead of curly brackets. Okay, let's start below here my data in the C. So we have here the first one added. So these are the local intercepts for each of the observations, and these are the local coefficient for temperature. What you have here is global. Locally, the objective is having them locally. Globally, geographically weighted regression. Here is global. While below here we have things locally up to the R square. Okay, if you need to add the coefficient for depth, how depth impacts pH, same thing, we call depth local coef equal DWR underscore model dot params, and then depth, the coefficient, the index is 2, x1, x2. Values. Sorry. We run, and then we come here, we check my data, and we see that def local coefficients are added to our data frame. Now, with head, we have it. Yep, yep. Oh, got it twice for intercept. Okay, so you first finish all of these, all the coefficients, then you run, and you get your data frame, and then you take it out, you print to your save to CSV. Yep. Now the last step, let's say call it was 6, so now it's going to be 7. It's 6 here, so what happened? 6. No, 6, step 6. Fitting model is step 5. Yeah, so it's step 6. Step 7 just is about the visualization. Visualization for that is mapping. Visualizing is better. Visualizing or mapping. Local coefficients. To let's take this out. Set mapping local coefficient for spatial variation, visualization. Okay, we want to visualize the spatial variation of the local coefficients. So that's what it means here. So we have my data.plot. What do you want to see? I want the column, which is our, let's say, T local coefs. Column equal to T local coef. Okay. And then the C map, color map. We have a color, and the legend equal to true. So these are the local coefficients for temperature, and you see how they vary along here, x longitudes here and y latitudes. So from the lowest to the highest coefficients, and you analyze them. If you want for depth, you see as well. Let's copy, paste here, and you change by depth, t by depth, local coefficient. Okay, this is what we have. So for our two independent variables, so how their coefficients varies across the space xy, longitude, latitude. So depending on your area of study, you see what are the impacts of your independent variables. Here is temperature and depth, how they impact pH locally across the geographic area. So geographically weighted regression. So sorry, we are already in the regression, but the purpose is really to stop here. Stop with the bandwidth. You need this first. Based on your y, your coordinate, your input data, your output data, and your input data, you need to have your specific bandwidth before you continue in this step. But I didn't want to stop just here for the video, so let's have a look at it. But the next video is going to about the regression itself. But still, when you run the regression, you have this is an absolute step. Okay. So thank you for watching this video. I hope it will help some people who are doing special statistics, geospatial analysis. So this is about groundwater data I have. You can use it on any special data you have. So okay, bye, see you next time.